And that's all okay?
Yes.
You can see, yeah, okay, great. Okay, yeah, hi everyone. As Zero said, I'm Gareth, if you don't know me already. I'm a final year PhD student, and I'm interested in massive stars, and particularly the multiplicity of them, how many are in binary systems and their kind of parameters and all that sort of stuff. So today I'm going to specifically be talking about the multiplicity of B-type stars. So to give you a quick outline of the talk, I'll introduce the topics of massive stars, massive binaries, and also B stars in particular. Then I'll go into detail in the first paper that we've published, which is on the multiplicity properties of the B stars in a galactic young open cluster called NGC 6231. And you can see that here in this quite nice X-ray image. After that, I'll talk about preliminary work that we are doing on searching for stellar mass black holes in the binary systems in this cluster. And then I can touch very briefly on future work to do with the rest of the B star sample in this cluster, and I can conclude. Okay, so first I should mention that massive stars are very important in astronomy and astrophysics on many scales, and this goes from individual exotic systems such as neutron stars and black holes, which represent the very end stages of these stars' lives, to the scales where they can impact entire galaxies through powerful mechanical, radiative, and chemical feedback that happens throughout the life cycle of a massive star. And we qualify massive stars as those as having more than 8 solar masses. The life cycle of massive stars is very different to that of solar-like stars, if you're familiar with those. In general, they live for millions of years compared to billions of years, for example, and they end up expanding into these red supergiant stars generally and ending their lives in catastrophic explosions known as supernova, leaving behind these very, very dense compact objects such as neutron stars and black holes. So this is kind of the general picture of massive star evolution. And we can look at a Hertzsprung-Russell diagram where we have the evolutionary tracks of single massive stars from anywhere down to 5 solar masses, which is more intermediate mass stars, up to 120 solar masses, which are the most massive stars that we know. And depending on the mass of a massive star, they evolve through different stages. So if we look at this zero-age main sequence, which is the black line, next to the values of the masses, we can think of this as a kind of birth line for these stars, where they start igniting hydrogen in their core. Stars more massive than about 16 or 17 solar masses are known as O stars on the main sequence. And those that are about 3 to 17 solar masses are B stars. And yes, that does include stars that aren't massive stars. So B stars represent this transition between the intermediate kind of star or more solar-like stars to massive stars. So in general, it is thought that B stars evolve to stars like red supergiants, and they become the largest stars in the universe by volume and become very cool, whereas O stars can enter these LBV-like stage, and LBVs are luminous blue variables, where we have these stars that undergo this episodic mass loss, eventually becoming stars like classical Wolf-Rayet stars, which have very strong winds, very high luminosities, and very high temperatures. So there's a lot of diversity and variety in massive stars themselves. There's a wrinkle to this, though, and that is that a lot of these stars are found in binary systems. For example, classical Wolf-Rayet stars and LBV-like stars and O stars have all been found to have more than 70% of a binary fraction. So 70% of these stars are found in binaries. So if we look at the initial stages only, so we have O and B, because I'm interested in stars that are on the main sequence. Yeah, O stars have been robustly studied, both in and out of the galaxy, whereas B stars, not so much. There isn't as many studies on these. But let's start on the O stars first. So we know that most O stars are in binary systems. And it turns out binarity is a very important aspect for massive star evolution, as a lot of these binary systems have periods that are close enough for these stars to interact throughout the lifetime of a massive star. These interactions can be anything from merging to envelope stripping to things like accretion. anything that changes the mass and chemical composition of a star is going to have a big impact on the evolution of that star. So yeah, these results were from a study that combined several time series spectroscopic campaigns of O stars in open clusters in our galaxy. So these are results for galactic O stars. One of these clusters is called NGC 6231, and this is in the Scorpius OB2 association. It's a young galactic open cluster with an age of between 2 to 7 million years old. And this means that the stars in there should be on the main sequence, and the stars in there should be near initial conditions. So they should be near the final product of the initial star formation in that cluster. Long-term high-resolution spectroscopy was performed on the 16 O-type stars that have been found in this cluster, and observed minimum binary fraction for these stars. So this is without accounting for observational biases, was found to be 63%, which is already quite high for these stars in particular. Several similar spectroscopic surveys of various galactic and extragalactic clusters have been performed in the past. For example, let's take the VFTS and the TMBM, which was the follow-up survey. So this is the VLT Flames Tarantula survey and the Tarantula Massive Binary Monitoring projects. And they characterize the O-star binary content in the Tarantula region, which is in the LMC. And this galaxy has a fifth of solar metallicity. So we can start to study binarity as a function of not only the mass of these stars, but also of the metal content of their host environments. Also numerous studies, as I mentioned, of O stars in galactic clusters. And I must stress that all of these binary fractions are the minimum binary fractions for these stars, and they do not take into account the observational bias. But when we do, we see that, yeah, a lot of O stars are in binary systems. In any LMC, 51% are expected to be in binary systems, and in the galaxy, 69% are expected to be in binary systems also. As I mentioned before, populations of B stars have been less robustly explored, and as part of the ERC multiples project here at KU Leuven, my work contributes to the B star part of the HR diagram above. Other projects in the multiples framework look at classical Wolf-Rayet stars, hydrogen-rich Wolf-Rayet stars as well, and O stars, but my work contributes to the B star part of this project. And there's a lot of reasons to characterize B stars like the O stars have been characterized. As I mentioned, they represent this transition between intermediate and massive stars as they go anywhere from masses of 3 to 17 solar masses. The formation channels for binaries across the range of massive stars is still fairly uncertain, and knowing the initial conditions of B star binaries, for example, on the main sequence can help. And there's also the fact that B stars are the archetypal massive star due to initial mass function considerations. So they are the most abundant massive star in the universe. As a result of this, they are also the primary progenitors for core collapse supernovae and of the further end of life stage, which is a neutron star typically for the early type B stars. So this also makes them prime candidates for producing progenitor systems for gravitational wave sources. So if we want to know the frequency, timing, and nature of both core collapse supernovae, of neutron star rates, and also to have a good picture of what can produce gravitational wave sources, looking at B stars at all the stages that they exist on throughout their life cycle is an important task. So what has been found so far for the multiplicity of B stars? Well, binary fractions for B stars so far have been found across a few different metallicity environments and ages. So we have the SMC, the LMC, and the Milky Way. However, and I also must note that these are bias-corrected binary fractions here. So this is what we expect the true binary fraction to be of these stars. But we still need more studies to disentangle the effects of age on the binary fraction of B stars, and also the effect of the metallicity environment on the what impact that has on the binary fraction and the properties of these binaries as well. And this is where my first paper comes in with these fellow co-authors, we studied the B stars in the Young Open Galactic Cluster NGC 6231 that I introduced before. It has a rich sample of galactic B stars, and as I mentioned, it has a high fraction of binaries observed in the O stars already. And so there's an early estimate for the B star binary fraction that was found to be 50%, though this was based only on 2 epochs of observations. So the more observations you can get for binary studies, the better, really, along with the duration and length of that observational campaign, because you can observe more kinds of binaries. There's also X-ray studies of this cluster that exist, and they estimate a large fraction of B stars to have likely pre-main sequence companions. So there's already some strong indications that the B stars in this cluster do have binary companions. So the sample of B stars we look at, they're 80 B stars, and they go all the way from 3 to 17 solar mass. So we have the entire mass range. And these are compiled from a previous literature study for all the B stars that have been classified so far. And as a result, this does mean that the sample is potentially incomplete, as it is based on what has been found to be a B star before. And most of them are dwarfs, which is what we would expect for a cluster of this age. So all of them are on, or most of them are on the main sequence. So what we first need to do is confirm whether these stars are actually part of the cluster or not, and we can do this with Gaia EDR3 distances. So we reject from the original target list, which was 84 stars, we reject that down to 80 based on their Gaia EDR3 distances. And now we have our target list of 80 B stars. So how do we do this now? How do we characterize their multiplicity? Well, we use a similar strategy, both observationally and regarding the analysis to what was done in the VLT Flames Tarantula survey and their follow-up studies. So this involves an in-depth analysis of VLT flame spectra, which is a multi-object spectrograph that retrieves low to medium resolution optical spectroscopy. And this is over, the original campaign was 31 epochs over 1.2 years. The setup that we chose provided us access to several suitable absorption lines that we use for radial velocity measurements. And here's a look at a 31 epoch combined spectra. So this is all 31 epochs combined into one spectrum of an SB1 binary. And shown here are the lines that we use to make the radial velocity measurements. So ones that you would expect from a B star are helium-1, for example, carbon-2, magnesium-2, and silicon-3. These are the kind of main stars that we use, main absorption lines that we used for RV measurements to measure their Doppler shift. And then there are a few lines that appear in the hottest B stars, such as helium-2. So they were also used on occasion for the highest temperature B stars in our sample. I mentioned there that the star was an SB1, and I should probably mention what that means. I think it's easier to start with explaining what an SB2 is, and it's what we expect to see when we observe a binary system in spectroscopy, where an SB2 is a binary where we can see both of the components of the spectral lines in the spectrum. And as both are moving in Doppler motion away and towards the observer, these absorption lines have this reflex Doppler motion in the spectrum, and they separate and come together as the star orbits. So an SB2 is where you can see both the primary component. In this GIF, it's A, and B is a secondary component. You can see both of these in the spectrum. However, sometimes you can't see the secondary component, and we call this a single line spectroscopic binary, or an SB1. And the secondary component can be missing for a variety of reasons, and this could be down to, for example, the secondary being much fainter and being much smaller, or it could be rapidly rotating, which means that these lines broaden, and as a result, they become very hard to distinguish when you are visually looking at the spectra. Another reason you might not be able to see the secondary component is that it might not emit light, and objects that don't emit light in these systems could be, for example, neutron stars or black holes, so compact objects. Or they don't emit optical, rather, I should say. Okay. So we've got our samples. We've got our sample. We've got our targets. How do we identify which of these stars are binary systems or are in binary systems from the spectra that we retrieve from VLT flames? Well, first we have to see whether these stars are variable in radial velocity or not. And how we do this is Gaussian or Lorentzian fitting of the radial velocities. Four radial velocities of the spectrum. So stars are identified as significantly radial velocity variable if any pair of them satisfies this 4 sigma variability criteria. And now we have a sample, a subsample of these stars that is radial velocity variable. Then what we do with the radial velocity variable subsample is search for periods in the radial velocities. So we do this with a Lomskargel periodogram. You can see here, for example, in this B0 dwarf, that we have a period of about 27.8 days. And if we find a significant periodic signal in these stars, we can take them to the next stage, which is to use that as an initial guess in fitting for their orbital parameters. This is the Dantley square method, where we fit the orbital parameters such as period and eccentricity and the rest of the orbital parameters. So here's an RV curve fitted with this blue line here. And it turns out, yes, it is about 28 days with an eccentricity about 0.3. So we do this for every star in our sample. And so we end up with all of these subsamples. So out of the 80 stars, we find that 12 of them are stable in radial velocity. 41 of them are radial velocity variables without a significant periodic signal. And so these two segments, we say, okay, these stars are single stars. Then we have stars that are radial velocity variables with a significant periodic signal. So we find a period for them, but we do not find a orbital solution for these stars. We have 7 of these. So we call these binary candidates, and we constrain the orbital solutions successfully for 15 single line spectroscopic binaries and 5 double line spectroscopic binaries. And we call these binaries. So yeah, we have categorized our sample into binary candidates, binaries, and single stars. And another way to get this binary fraction now is to separate objects whose radial velocity variations are probably dominated by pulsations, for example. B stars do very frequently have pulsations, and quite strong ones too. And we want to find a subsample of these stars whose RV's variations are dominated by the orbital motion only, or not only, but yeah, are dominated by the orbital motion. They can still be pulsating and they can orbit at the same time, but we separate this into single pulsating stars and orbiting stars that are orbiting in binaries. And so we adopt the same variability criterion from earlier, and we adopt and fix this threshold velocity for an RV amplitude of 20 kilometers per second for detecting binary systems. And this adoption of the threshold is fairly arbitrary. You can see it does separate into 2 populations in this graph here, but it is fairly arbitrary, but this is taken into account in the bias correction. So we start off with this observed binary fraction of 33% here. And we can compare this to the observed binary fraction for the OS type stars in the very same cluster. And we can see that it is almost double, it's much higher. But it's important to take into account here that these are not corrected for the observational biases. So now we have our observed binary fraction for the stars. We can start investigating this a bit more. And we also know that we have B stars from almost the entire mass range of B stars. And we find this from doing spectral classification of these stars, and we do this comparison with standards that have been observed by Hermes, mostly. And you can see on the top left, in black, we have single stars. In yellow, we have these binary candidates I mentioned, and in green, we have objects with binary solutions. And you can see that there's this kind of suggestion of a trend here where from B0 to B4, for example, the binary fraction seems to decrease. There could be an incompleteness effect here where we don't have enough information on the but we don't have a complete population of the latest B stars in the samples, so the B7s, B8s, B9s, for example. So what we can also do is look at the brightness distribution of the stars, and you can see that this trend becomes more pronounced. The bottom bounds of brightness distribution, again, could also be subject to the most radial velocity scatter, which because the most dim stars will have the noisiest spectra. It could explain the increase in radial velocity candidates, for example. But yeah, so these are both probably affected by biases, but there is a suggestion that, well, if binary fraction is increasing with brightness, there's potentially an dependence of mass on the binary fraction might have a mass dependence. Yeah, so that was the observed binary fraction, but we want to find the true intrinsic binary fraction for these stars by accounting for these observational biases. So I'll just describe the two main biases we correct for here. The first one is purely observational, in that we are limited by the orbital parameters we can observe based on the observational campaign itself. Let's take the length and the cadence of the campaign, for example. So the length of the campaign is about 1.2 years. And that means that we aren't going to be able to resolve binaries that have periods that are much longer than this. So we're kind of limited to about a year here. So to do this, we generate, to correct for this observational bias, we generate a set of simulations to correct for it. And you can see that depending on the mass ratio here, which is on the y-axis, and that's the secondary mass, the small star over the primary mass, the larger star, the more massive star rather. You can see that depending on that, we are sensitive to periods of only hundreds of days. Yeah, so that's the first observational bias. And the second one we want to account for is what we call the SB2 bias. This is particularly due to the relatively low resolution of our spectra. And I'll just walk you through what we have on the right here. So we have two simulated spectra. The top ones, and they're both B0 plus B0 systems. So they're equal mass. It's an equal mass binary system. And at the top, they're separated by radial velocity of 100 kilometers per second. And in this case, you can see that the two line profiles are actually blended and appear as one component at the same wavelength. Whereas you can see if the radial velocity separation is higher, for example, at 280 kilometers per second, you can clearly see that there are two profiles here. So this line blending of particularly equal mass binaries can dilute or completely mask the apparent Doppler motion of the primary scale. So what we do is we use these simulated T-Lusty spectra of binaries of various mass ratios, measure the radial velocities of these, and from this we can simulate the effect that this has on the detection of our binaries, where our detection threshold is 20 kilometers per second for a radial velocity amplitude. Okay, so if we combine these biases, so we combined it with the effect of the SB1 bias, you can see, as I said, particularly for equal mass binaries, right at the top on the y-axis, that the impact is pretty bad. Line blending does become a real issue here. So it's definitely something that is important to take into account. So if we integrate this detection probability of all the periods that we have, then this gives an overall detection probability of about 63%. And this gives us a bias-corrected binary fraction of 52%. So let's compare this to the bias-corrected binary fraction for the galactic O-type stars, which is 69%. And with the errors, they are only just in agreement. So this does pretty much suggest that, yeah, this is another suggestion of a mass dependence on the binary fraction. Yeah. Okay, so this bias-corrected binary fraction brings it in line with other bias-corrected binary fractions for B stars, both in and out of the galaxy and of, yeah, so for example, we look at 30 Doradus, which is in the LMC, and we look at Cygnus OB2, which is in the galaxy. We have similar bias-corrected binary fractions, and we also have similar fraction for the field B stars as well. However, none of these are corrected for the SB2 bias, so these binary fractions could be higher, but one that has been corrected for this SB2 bias I detailed was NGC 330. And this is a much older cluster of 35 to 40 million years compared to 2 to 7 million years for NGC 6231. And you see it has a much lower binary fraction of 34%. However, this is in the SMC, and so we need to take into account, we can't disentangle the effects of age and metallicity here on the binary population, but it could suggest that this binary fraction decreases with age, potentially due to things like post-interaction products, like mergers, which can reduce the binary fraction over time. Okay, so we've identified all these binaries, and now this allows us to construct new orbital parameter distributions for these B stars. So we have periods of 1 to 260 days. As I said, we can't find periods much over a year here. You can see in the black crosses is the observed period distribution, and in the blue crosses, we have the bias-corrected period distribution, which we calculate from the detection probability we find from the bias correction. So below 30 days, the period distribution is nearly unbiased, but above 30 days, we are likely missing longer period systems, and these might appear as radial velocity variables in this study. So more observations of this cluster could perhaps confirm that and bring up the observed binary fraction, but we do account for this in the bias correction. So we can compare this observed binary period distribution here to both O and other B star populations and those that are in and out of the galaxy. Once we do that, we can see that they're all quite similar. And statistically speaking, there's nothing much here to challenge that there seems to be a general universality of period distributions across both mass and metallicity. And this could suggest that there's some kind of universal formation process for stars, regardless of their mass and their metallicity in massive stars in particular. However, as I keep saying, more samples are needed to verify this because we need to disentangle these effects of mass and age by having enough examples. And we find that the same is true for the eccentricity as well. We find that there is no significant difference between the samples in their eccentricity distribution. Okay, so we've identified the binaries in this cluster, and now a useful question to ask is, what kind of companions do these SB1s have? And the reasons to investigate this question are twofold. So you might remember that I said that SB1s are lacking a secondary signature, potentially due to the observational bias I've mentioned. If the secondary companion is faint or rapidly rotating, or if potentially they are a companion that emits nothing in the optical, and so that they might be compact objects. And so as we characterize the unseen companions in these SB1s, we are probing the low mass end of the companion mass function, and we can find systems with more extreme mass ratios, and we can go past the limits of our original observing strategy. And while we're doing this, we can also search for compact objects like black holes and neutron stars that could reside in these systems. So I'll go over the first point first. So yeah, from the study, the first paper, we only identify 5 double-line spectroscopic binaries visually. And this is a small sample size. We can't really discern much from this or compare it to other observed distributions. However, we can probe more extreme mass ratios past 0.5, we can see here, and the mass ratio again is the secondary mass over the primary mass of the stars. And we can do this via spectral disentangling, which I will go a bit more in depth in a bit. But once we do that, in this sample alone, we can see that we can go down to mass ratios of 0.1. So much past the limits of the original observing strategy. To touch on the second point, we should introduce the subject of compact objects in binary systems. So we know that gravitational waves have shown us that tight pairs of compact objects do exist, like black hole plus black hole systems, for example. And there are two main evolutionary scenarios for the formation of these objects. The first one is that both stars in a close binary system undergo chemically homogeneous evolution. And this can prevent mass transfer in these very close binaries. And this allows both of these stars to directly evolve into black holes. However, this favors low metallicity and pretty massive stars that are over 30 solar masses. So that should be noted. And a second main proposed pathway for these black hole plus black hole systems is a result of mass transfer via Roche-Lobe overflow. And this can happen in a system leading to common envelope evolution, where these two stars share a common envelope. And this can produce black hole plus black hole or black hole plus neutron star systems, for example. So these are the two main ones. There are a few other proposed pathways for these systems, but I won't mention them here. But observational constraints are needed to validate these pathways. So we need to observe binary systems at all stages throughout their evolution in order to validate these. So yeah, how many, I think a good question now to ask is how many do we expect to find? How many stellar mass black holes do we expect to find in these binary systems? And recent theoretical computations predict that about 3% of massive O or early B stars should have a dormant black hole as a companion. So where are they? Have we observed any yet? As I said, gravitational wave detections of black hole plus black hole systems exist, which leads to the discovery of 100 stellar mass black holes, and this number is increasing as gravitational wave astronomy continues to grow and grow. About 100 compact objects in general have been detected in X-ray binaries, and these are detected in the X-rays because the compact objects in these systems are accreting material from their high or low mass companions through Roche-Lobe overflow or wind accretion. However, only a handful of these are black holes. That should be noted. And the only X-ray quiet massive star plus black hole companion found with certainty so far is MWC 656. And this is a BE plus black hole system where a BE star is simply a B star with a mission. And this is thought potentially due to that B star having a disk from rotating very quickly. Okay. It should also be noted that there are several reported quiet OB plus BH systems in the last couple of years, and these include LB1, HR6819, NGC 1850 BH1, and NGC 2004-115. But it must be stressed that all of these have been challenged by subsequent studies, which really does highlight how difficult it is to find these systems with certainty. But we're going to try anyway. With the SB1s in the NGC 6231 B star sample. So all of this going forward now is preliminary work towards a second publication. So as I mentioned before, we can perform Fourier spectral disentangling, and this is part of our first step where we need to see if there is a signature of a faint companion in the spectra that we observed, so the composite spectra of the primary and the secondary star. So Laurent May has been doing this for the SB1 sample in the NGC 6231 B stars. And during this process, orbital parameters are kept fixed and the primary and secondary RV amplitudes are varied. If there's a faint companion in this process, we expect to extract a secondary companion which has star-like features, like in this example here, where we have the composite spectra on the top. There's 5 epochs of them, and on the bottom we have the primary star and the secondary extracted secondary extracted spectrum. Otherwise, if there is no features in this secondary extracted spectrum, or there can't be a constrained solution, then the secondary could indeed be a compact object in this case. So now that we have, wait, oh, I'm sorry, I'm missing a slide. If I could just briefly pause. I do not know how this happened. Okay, I'm just going to have to continue. That's fine. What I was going to say out of this is that out of the 15 SB1s that we have 7 that we find spectral companions, secondary companions in. And so 7 of our 15 SB1s are actually SB2s, and these are the ones that you saw in the mass ratio distribution earlier. And then we have 4 stars that are we have ambiguous results on and require further studies, but these still could be candidates for those harboring a compact object. And then we have another 4 stars where we cannot find any signature of a secondary companion in their spectra. And so we have 8 stars now that do have some potential to harbor this compact object. However, 3 of them are 3 mass. Some of them are 3 of them are B9 stars, which have 3 solar masses. And from the constrained orbital parameters that we have from this star, if there was a black hole or neutron star in these systems where the primary star is such a low mass, we should be able to see this from what we call the binary mass function. And we simply do not see that, so we discount these. So we have 5 individual candidates, and you'll see their names shortly on a subsequent slide, where we think that they could be harboring a compact object. So now that we have some candidates, we want to find the range of masses that this unseen companion could be. And how do we do this? Well, first we need to find an estimate of the primary mass. And the first way we can do this is to find a spectroscopic estimate of the mass. So this is a preliminary example with one of the stars that we couldn't find a secondary companion for in spectral disentangling, and this is HD 152200. And this fitting method is adapted from an implementation by Bodensteiner, where we take a grid of T-Lusty models for these stars. Both we have a B star grid and an O star grid. We combine these, and we fit the observed spectrum against this grid of T-Lusty models to retrieve TEF, log G, and V sin I. So from this, yeah, we have constraints on TEF, log G, and V sin I from this. And what we could also do is a photometric fit using the same method, but instead of comparing with spectra, we're comparing with SEDs. So this is a photometric fit to the SEDs, and our 3 parameters here are TEF, log G, though these aren't as well constrained as they are for the spectroscopic fit, because it's very difficult to do that with SEDs. But we also fit for radius, which is needed to calculate the luminosity, and we fit for the extinction to the source as well. So for this, we use various sorts of photometry, including 2-mass and Gaia, to fit the SEDs of these SB1 stars. What we can do now is combine the chi-squareds of both of the fits to give us strong constraints on TEF, log G, V sin I, and the radius and the extinction as well. And from this, we can calculate the luminosity of the star as well as the spectroscopic mass of the primary star. So this is one estimate of the primary mass of the star we have. But we do have another way, which is to find the evolutionary estimate of the mass as well. We do this with BONNSAI, which is a Bayesian statistical method to determine fundamental stellar parameters like TEF and log G and the evolutionary mass and ages of these stars. And it compares all the observables that we found from the spectroscopic fit to a grid of galactic stellar evolutionary models. On the right, we plot the spectroscopic mass estimates against the evolutionary mass estimates for our best candidates, and you can see that there's some discrepancy, especially at higher spectroscopic masses between the two. And so it's important to find, in this case, two sets of unseen mass ranges for these binary systems to compare them. Okay, so we have our primary mass estimates. How do we find the range of possible unseen masses for these unseen objects? Well, with the primary mass estimates and the radii of the stars fitted already, we can first of all compute the critical rotational velocity of the visible star, which is the maximum velocity a star can rotate according to its mass and its radius. And as such, also having the projected rotational velocity of the star, we can find a lower limit on the inclination of the system. And so once we have this lower limit on the inclination, we can then find a range of possible masses of the unseen object with the binary mass function. And we also input the measured orbital parameters that we have from the first paper and the mass and radius estimate of the visible star, and we can derive this range of possible masses. So the example on the right is taking the evolutionary estimate of the primary mass. And as a result, you can see that the mass of the unseen object to this star could be anywhere between 1.2 and 2.5 solar masses. Okay, so now we can compare these ranges to the predicted mass range for galactic neutron stars, which is in red in this diagram, and galactic stellar mass black holes, which is in blue. And you can see that the star we've been looking at, HD 152-200 on the way on the left, could potentially be harboring a neutron star. So now we know what potential unseen masses this star could have. We now need to see through detailed simulations whether we can hide a couple solar mass star in the spectrum of HD 152-200. However, the most promising candidate amongst these five for harboring a black hole is CD 411103A. And this star in particular was one that had an inconclusive result on its spectral disentangling. But you can see from the range of spectroscopic masses and evolutionary masses, for example, that we do have potential for some quite significant masses of the secondary star. And in this case, it would be very difficult, regardless of the inclination of the binary system, to hide masses this large in the spectrum. Okay, if the compact object was a star and not a compact object, that is. So this requires further study. All of these candidates require further study, and I must stress again that this is preliminary work. Okay. All right, I'd like to summarize now. In our first study, we characterized the multiplicity properties of the B stars in NGC 6231. And from this, we found a bias-corrected binary fraction of 52%. We also found some indications that there's an increasing binary fraction with increasing mass. And there seems to be this general universality between observed distributions of OB stars for their orbital properties. And so there seems to be some suggestion that these binaries form in very similar ways, regardless of their mass and of their metallicity. And to summarize our preliminary work that we are doing now, we're currently determining the unseen companions to the SB1s in that sample. So we're extracting any faint companions from these spectra through spectral disentangling. And with those stars that we can't extract a companion from, we can do atmospheric and evolutionary models to determine the minimum mass, the potential minimum mass range of these unseen companions in those SB1s. And so far, CD 411103A is the best candidate right now in our sample for harboring a black hole or a compact object in general. Okay, so very briefly, I just want to touch on what I'm going to do with the rest of the sample. So we want to extend this atmospheric and evolutionary fitting basically to the rest of the B-star sample, including the SB2s we identified in the first paper and also the 60 single stars that we have found. Why do we want to do this? Well, first we can compare the rotational distribution of the sample, for example, the rotational velocity distribution of the stars, how fast they rotate, to the stars of other older clusters, and potentially those in different metallicity for environments, for example, as well. So we have on the right the rotational velocity distribution of NGC 330 and that of 30 Dor. And NGC 330 is, as I've mentioned earlier in this talk, anywhere between 35 and about 45 million years, I think. And then 30 Dor has kind of a max age of its stars in the LMC, so not in the SMC like NGC 330 is. 30 Dor seems to have a maximum age of about 15 million years. And so you can see that there appears to be more quickly rotating stars in the older cluster, in the blue, than in the purple, which is the younger cluster. And this might be an imprint of binary interaction, as when a star gets older and these stars interact throughout their lifetimes, they can spin up their companions and we see more quickly rotating stars. So we can compare that with the rotational distribution of our young galactic cluster, for example. We can also use BONNSAI again to find evolutionary masses and ages of these stars, and then we can construct an initial mass function and describe the star formation history of the B stars in this cluster. And we can also compare this with previous work done on the star formation history of NGC 6231 in general. So yeah, that's it for me. Thank you very much for listening. Sorry about the hiccup in the middle. I'd like to receive any questions that you guys have. Thank you.
Thank you very much, Gareth. It's very clearly a lot of work. Also very nice talk. Are there any questions? So if there are questions, please state your name in the chat and I will call you. Apparently, yeah, Pablo.
Hey, Gareth.
Hi, Pablo.
Question. So regarding the black hole candidate you have, what's the eccentricity of it?
That is a very good question that I will have to get back to you on, because this was kind of put together over the past couple of days. I've not looked at the eccentricity, but I will definitely get that back to you.
Yeah, as you might know, I care about the eccentricities in terms of constraining the kicks in this. This type of objects.
Sure.
And the other thing I wanted to ask regarding the other candidate you have that more or less goes from the neutron star to black hole range. So this is more a comment than a question. That whole part you have between neutron stars and black holes is a region that's uncertain whether or not black holes cover. So theory predicts there might be a gap between these two, but from LIGO data, it's unsure if it's actually starting to get populated. So if more or less, if you find a black hole that's sitting there in the middle, this is a very important discovery, even though it might look like it's not a very massive thing or anything. So I just wanted to point that out.
Yeah, that's definitely something to keep in mind, and it's something that I have also heard of as well. So yeah.
Cool. Well,
yeah, thank you. Yeah, thank you.
Okay, then I'll go from young to less young. First, Nick.
Yeah, hello, Gareth. Thank you so much for the talk. Very nice. Hi.
Thank you.
I just have a general question, actually. Because I'm not in the field, but I was just wondering, like, do formation simulations of open clusters, do they agree with what you also find of the multiplicity of O and B stars?
That is also another very good question that I cannot answer. I definitely need to, I think that's something that will come with looking at this star formation history of the entire sample, because so far I've only constrained, for example, the evolutionary information on, well, here's 5 stars and there are 80 stars in there. So that's definitely something I want to look at and see, compare what has been predicted for formation models of open clusters, for example, with what we can find with the stars in this sample. but that's definitely something I'd want to look at. Yeah.
Okay, thank you. Very cool.
Thanks.
Okay, then next we have Simon.
Hi, Gareth.
I see.
Hi, Gareth. Very nice talk. I had a question on the first part of your talk.
Yeah.
Where you talked about this cutoff that you do of 20 kilometers per second to make sure that you don't measure the pulsations because, yeah, as you know, many of these stars are pulsating.
Yeah.
Regarding that, I was wondering what lines are you using to do the RV calculations? Because, yeah, as you might know, some of them are more sensitive to pulsations than others.
Sure.
And does this have an effect on your RV precisions or whether you can maybe lower this boundary or not?
Yeah, sure. So what lines I use, I can answer that. I've used helium-1 lines, and I think the line you're referring to that could be particularly sensitive to pulsations is the silicon-3 line. I know that this can show a lot of variation. This is used in some cases, but I do look, this is on kind of star-by-star basis. Looking at these silicon-3 lines, it's quite obvious when you can see that there's strong line profile variation from epoch to epoch in the silicon-3 line especially. And in these cases, I don't tend to use these because there is quite an obvious signature in the of pulsational activity in this line. So other than that, I don't really think that there are many lines that that's susceptible, or at least whenever I see line profile variations that are quite obvious, I don't include them in the range velocity measurements. But yeah, as I say, the actual selection of this 20 kilometers per second, this is corrected for in the bias correction, as this is our detection limit that we can use in the bias correction. So it is still quite an arbitrary choice, but at the end, it doesn't really matter when we take the bias correction into account. But it definitely is interesting to find if we can reduce this. And there are further studies, I believe, that are being done on how this threshold velocity can change with the luminosity class of the star and also the spectral type of the star as well. Mm-hmm. So this can vary quite a lot. I think it's gone from anywhere from like 5 to 30 kilometers per second for these stars. So yeah, it's definitely something I'm going to keep an eye on. But for this study in particular, I don't think it's going to be a problem. Yeah.
All right. Yeah. No, doesn't seem so. So thanks.
Thank you, Simon.
Okay, then we have Hans.
Yeah, Gareth, I have a question with respect to the SB2 correction bias.
Yes.
Can
this slide?
Yes, this slide, because so if I read this slide.
Sorry, Hans, we can't hear you.
Oh yeah, you're a bit quiet, Hans.
Is it better?
I think that's a bit better, yeah.
Much better?
Yeah, that's much better.
Much better.
Great.
Okay.
Thank you.
If I look at this slide, I would think that, so for short periods, you have a strong bias for independent of the mass ratio, but with short periods and mass ratio of 1, I would expect that in one phase you will overlap indeed, but it will be a quite high amplitude. So I think you would see that easily in your time series. Yeah,
I agree.
So why is that a high? So why is this curve formed like this curve?
Sure. Yeah, so from 1 to 10, yeah, it does drop off quite quickly.
I can give you the answer.
If you want to give the answer,
The amplitude of the radial velocity need to be larger than the typical full Louis-Half maximum of the lines. And we're dealing with massive stars that rotate over 100 kilometers per second on average.
Okay.
And when you sum up 2 lines to Gaussian that are identical, as Gareth shows, it looks like it's the same Gaussian.
Yeah.
It is a quite shocking fact when you make that plot for the first time, but it is actually a big bias that is often neglected.
Even if the amplitude is large, because the lines are much broader than the amplitude.
The radial velocity amplitude of the binary need to be quite a bit larger than the full Louis-Half maximum of the lines of the rotations.
Okay. Yeah.
So
it's really on the rotational. So it's really the line profile that plays a role there.
It's the line profile. So either rotation or resolving power, right? But
But
once you resolve the line, it is its rotation that dominates.
Yeah. Okay. So it's really the rotation that is important there. Yeah. Okay. Thank you.
Thanks.
Okay. Does anyone else have a question for Gareth? If not, then I think we can close. So it's thank you very much, Gareth, again. And so this was the last talk of this calendar year. We will be back in January. See you there then. Bye.